welcome to all of the attendees for this last security seminar of the summer. We've had a great series of speakers over the summer, and we've built up to this finale that a friend of many of us, colleague who's been in the field, pioneered a number of things on the faculty at NYU, but responsible for online programs, real programs, research, student competitions, conferences, all kinds of things in the area of cybersecurity that have helped grow the field. And he's going to share some thoughts with us today, given that background, on AI, computational imaging, and the battle for media integrity. So welcome to Nasir Memon, and please take it away.
Thank you, Ed. You can hear me, right?
Yes.
And I'll share my screen to get started and go in presentation mode. Okay. Oops, sorry. It's slow to respond. So good afternoon, everyone. I guess it's afternoon there as well. I'm speaking here from Brooklyn, New York, and it's a very, very hot day outside. I don't know if it's the same in Lafayette. And actually talking from my office. I mean, I'm back at work, and it's fun to be back after such a long gap. So this afternoon, I'll talk to you a little bit about what I guess people in the news these days are calling as the media integrity crisis, although crisis may be a strong word, but nevertheless, there are issues that we are facing today, and we expect that perhaps things will go worse as they go further down the road, and that we should be doing something about it before they get worse, right? And so I understand, I very much know the center, it's CERIAS, right? One of the things, I started a center at NYU, and I thought we should become like CERIAS, right? So, and I don't know about the great work in cybersecurity that you do. And I understand a lot of you could be from a computer science background. At the same time, I feel a bit nervous that you have someone like Ed Delp sitting out there listening to me, who's a founder of this field, really. He's been at it for a very long time, and I've kind of worked with him and have learned from him as this field matured, right? So, and it sits more in the signal processing kind of world, and so I'll try to kind of talk about things at a reasonably high level, and also try to be sensitive to the fact that there are computer scientists in their audience, and try to get across some main points, right? So basically, I'll talk about what the issues that we face today briefly, right? I don't want to dwell too much time on that. Talk a little bit more about some of the key things that we have done in media forensics, right? For almost 2 decades now, some of the key techniques and what now is emerging in the sense of how imaging is going neural, in the sense that a lot of machine learning techniques have really transformed computer vision and imaging, and how that's impacting, how can impact media forensics, and how perhaps we can leverage it to sort of provide authenticity to media. So as I said, media forensics is the issue of whether this media is authentic or not has been around for a long time, because even when things were not digital, right? But especially when things went digital, the advantages to having sort of images in digital form, right? It brings down the cost, scale, you can share them and all that stuff. But it also allows us to manipulate them, change them. And for a long time, it was done for fun, right? When we started working on it, people like Ed and me, like a long time back, in the early 2000s, right, we were more worried about law enforcement point of view, right, whether this image is submitted as evidence is real or not. But today it's kind of now being used for misinformation and propaganda. And also over the last few years, it's also sort of there's disturbing trends of fake images being used in the scientific literature, right? And Ed is doing a lot of nice work on that, scientific reports and for clinical trials and things of that sort. So, and a lot of that is being driven or fueled by the fact that we have better capabilities, right, to manipulate images using machine learning techniques, and it can be done in a shorter time at lower cost, right? So what this has led to what some people call the democratization of synthetic media as well. I mean, synthetic media also has been around for a long time. It's also known as Hollywood, right? Hollywood isn't the business of creating media that's synthetic, right? And gives you the illusion of something being true when many times it's not. So although image manipulation has been around for a long time, the recent advances in machine learning have also made it possible for us to develop what we now know as deep fakes and cheap fakes. And you've seen all that stuff in media, and I won't repeat it, right? Now we are also, like, in the sense it's going to the point where when I say democratization, it's available as a service, right? Service in the sense that companies out there, both overground and underground, whereby you can say, hey, I want a deep fake or Nasser Memon doing this, and for $50, $100, $500, right? The prices, depending on what you want, you can actually get it done, right? So it's available as a service. There's also an app there, not very good, right? But still, the fact it's a starting point whereby I can replace myself, right, in real time on a video conference call. So for all you know, 10 years later when I'm speaking, perhaps it's my postdoc speaking, but because I'm busy in Hawaii taking a vacation or something, but actually you can deep fake and appear as if it's me speaking and have somebody else do that instead, right? So we are getting to that point where it's just not Hollywood and nation states that can do this, but anybody can, not almost anybody will be able to do that. And that's a problem, right? And of course, nation states being able to do that at scale to create misinformation leads to problems. It leads to polarization in society. It leads to deaths. I mean, there are people who have died in India because of fake images or fake video. And what do we do, right? So one of the answers to that is, of course, media forensics, right? Media security broadly, and media forensics as a sort of a subset of media forensics as a subset of media security, right? And the kinds of questions that we've traditionally answered, right, over a long time was, hey, given a picture, video, is this real or is it generated using computer graphics? And this question of graphics of video has been around for more than a decade. Graphics are real, captured by a camera, has been around for more than a decade now. But now with synthetic images that can be generated using machine learning techniques, the problem has gotten more difficult, right? And again, a harder problem is, has this photograph been manipulated, right? And this is hard because we do kind of quote unquote manipulate images, right, for benign purposes. And what's the line between sort of malicious manipulation and benign manipulation? When can you say it's authentic and when you say not? It's a blurry, fuzzy line. And so it becomes harder. And of course, if the manipulation is tiny, it becomes harder to detect it. So that's even harder, right? And then there's also the attribution problem that we've always talked about, right? So something about provenance, where did this image come from? Where did this video come from? In sense of which camera, what date and time was it taken? What place was it taken? right? Things of that sort. People have we have studied for a long time, and that's kind of what we've been doing in media forensics, right? And why this essentially works is because, and I'll talk about images, but a lot of what I say applies to video as well, right? and essentially because when you manipulate any media and insert an object in it, like this car out here, I hope you can see my cursor, right? We go through certain sort of steps, image processing steps, and those steps sort of leave some telltale artifacts, right, that allow us to potentially detect the fact that the image may have been detected. And where do these artifacts stem from? Where do they come from? Well, they come from the fact that the image is not produced magically, right? It's not that you press a button on the camera and boom, an image is produced, right? There's actually a long and quite a computationally intensive processing pipeline that uh, the sort of light from the scene, which is then captured and converted, right, into these pixel value, when you convert photons to electrons, intensity when you measure, and then you render that whole thing into a nice looking, visually appealing image that involves many different sort of image processing steps, right? And this is called the imaging pipeline, right? That happens within the camera. And of course, in the past, you had to buy a big and expensive camera to sort of have a reasonably powerful imaging pipeline. But these days, with a sort of camera which is in your cell phone, right? You actually have a lot of computational power in there to implement complicated sort of image pipelines, right? And these sort of leave certain characteristics, broadly speaking, right, in the image. And when you manipulate an image, sort of the consistency of these characteristics gets disturbed. And that's what we are doing. We are doing statistical analysis, and we are sort of trying to detect the fact that there's a break in consistency of these characteristics, or there's a certain type of consistency in this characteristics that tells me that it's a Sony instead of a Canon and things of that sort. And this is all what we call signal processing. And in Purdue, you have a phenomenal signal processing department with some very well accomplished people in there. And you can go learn a lot about this from them, right? And so let me just give you, for those of you who are new to media forensics, and with apologies to those who know about all this, let me just give you some simple example, right? One simple example, which has been, in my opinion, quite successful. Something we call sensor fingerprints, right? Which, or also the photo response non-uniformity, or PRNU noise, right? And there's some others also, which I'll go through quickly, but I'll talk about PRNU in a bit more detail, because intuitively it's sort of easier to capture, right? Understand. So essentially, the PRNU noise essentially is kind of a noise pattern that gets embedded into every image taken by a specific camera. And this noise pattern is unique. I know unique is a strong word, but quite unique, right, to the specific camera, right? In the sense that my iPhone will have a different noise pattern as compared to your iPhone, although they may be the same model, bought from the same store, same day, whatever, right? Two different instances of the device will have different noise patterns. And that are essentially, they come from the fact that the underlying sensor, right, the imaging sensor, right, which senses light, right, and converts those photons into light intensity electrons, so that in some measurable format, right, we are able to, that response kind of varies because of no two physical sort of gizmos are exactly the same, right? And so there'll be a slight variation. And a good analogy for that is what we call, you must have you would probably know about from reading detective novels from your childhood days, right? We call it about gun ballistics. So when a bullet is fired through the gun, right, as the gun sort of traverses through the gun barrel, Each gun barrel, although same model, make, etc., right, has slightly different distortions in it, deformations in it, which causes unique scratches on the bullet as it sort of traverses through the barrel. And then when you have a fired bullet, right, and you have a gun, you can actually test it out, fire 20 more bullets, see what the scratch patterns that you get, and compare that template scratch pattern with the bullet in question, query bullet, and say, yep, this bullet was indeed fired from this gun. Surprising thing, as I said earlier, is you can do this with cameras. So you can, given an image, given a camera, you can say, yep, this image was taken from this camera. And it's been quite successful. And to my knowledge, one of the few sort of forensics techniques that was accepted in a code of law, right? And the FBI studied it quite thoroughly and said this works with high accuracy. And so not just attribution, but it can also be used for sort of being able to tell whether an image is authentic or not. So if you have a camera from which a particular image may have been taken, and you have the image, you can get the fingerprint of the camera, match it, and see if there's mismatch in a particular part. You can say that, hey, this image, this part of the image has been manipulated. And there are other applications as well, right, that it can be used for. And the noise pattern itself is what we call is nonlinear, right? So you have the observed pixel value, the measured pixel value within the camera, but it's actually a function of the unobserved clean pixel value that came in through the lens, right? And that is then perturbed by this PRNU, which is not additive, it's multiplicative, it's nonlinear, plus there's other sources of noise as well. So there's a clean value, X, and then the value that you actually get when you get the photograph. And this is where that PRNU is sitting at, right? And because of this, it's kind of hard to remove, and it survives many linear operations, right? And that has been the source of its success, if you will. And the way, as I said, it can be used for detecting photo manipulation as well. So here is an image, and the circle red parts are the manipulated regions of the image. And suppose you do have the camera from which this picture claims to have been taken, you can extract that fingerprint and match it with the fingerprint in the image. And there's certain parts, these parts, you'll see that the match is poor. A dark spot means a poor match, right? So that kind of pulls it out for you that these two are actually, these parts are manipulated, and you're able to localize the tampering, that this was perhaps added, and this was removed, and this was added, and you're able to detect both removal and addition of artifacts. And of course, there's a lot more to it. How do you detect which part? How do you grow those regions? There are different techniques that can be used, and it has some reasonable sort of accuracy in what we call localizing the manipulations, right? Because you need to localize. Just saying whether an image is manipulated or not is not enough in many applications. You want to actually be able to even say what part of the image was manipulated. And so this works great, right? But there's certain issues with it, and many of you who have a security mindset, probably it's already jumped in your head saying, what the heck? If there's a fingerprint, why can't I simply spoof it? Why can't I take an image, extract its fingerprint, and then put it on in another image, take an image from Nasir's camera and extract that fingerprint from it, and then put it in some other image and claim that Nasir's camera took it, right? Yeah, can be done, right? Not that easy, but by a skilled manipulator, skilled person, it can be done. So that's an issue. The other issue is the privacy leak, right? So you can't just post an image. You can imagine many of the Black Lives Matters or the other protests that you see sometimes, right? Pictures that captured scenes that we saw. Maybe in some of those situations, the folks who took the picture, don't want to be known that they took the picture for whatever, for fear of reprisal or something of that sort, right? But the presence of that fingerprint is a problem because it can actually end up revealing as to who took that picture. Right? In some situations, that may not be ideal. Right? Also, it's not very reliable if the image is dark. It's more or textured. It's more reliable in flat and bright parts of the image. And the precision of the localization that I showed you earlier is kind of limited, right? The objects in that picture that we detected as manipulated were quite large, right? And perhaps one of the most problematic aspects of it is that it is of limited robustness. As you start compressing the image, as you start scaling, cropping the image and doing other transformations to it, its accuracy starts dropping. Although it's better than many other forensics techniques, but it does drop tracking. So those are the problems with it. So and also it's not very scalable because a fingerprint can be very large, right? So that's one approach that has been successful, and even today people use it for image forensics analysis or video forensics analysis. There are papers written literally every week on this still, right? As an active area of research or improvements and things of that sort. And then there are others which I'll quickly run through. I apologize because I'm mindful of the time. So one of the other things people look at is compression traces, because when you manipulate an image, you compress it again, and there are multiple compressions that take place. And so because of that, certain parts of the image have different statistical characteristics as far as the JPEG sort of representation goes, and based on that, again, you can detect. A third way of detecting has been what we call copy move forgeries, right? So often it's done, right, where, and these are some well publicized sort of images from the past, where it was somebody manipulated an image to show more than what actually happened by simply copy pasting some parts of the scene to another, and copy pasting also we've been reasonably good at detecting it, because basically intuitively you for the computer scientists, you do a comparison, you do a cross correlation, if you will. You want to be more efficient than that. And you find areas that are very match very well, and you say, hey, that's a problem, right? And you can detect them. And then finally, these days, especially with machine learning techniques, there are lots of approaches being used whereby you actually look at the image residuals after doing some filtering, and many of those manipulation operations like compression or pasting or scaling or cropping or brightness, etc., all the adjustments that a manipulator has to do will result in kind of a perturbation of these residuals. They will not be consistent. And these days, with in the past, we were trying to develop models to detect them, but these days, these powerful machine learning detectors can actually pull them out pretty quickly, right? So examples for it, like this part of the image has been cropped. It has a different residual sort of pattern as opposed to the rest, right? And so this has been done, but the problems, of course, are, as I said before, when I was talking about PRNU, they are sensitive to post-processing. They have been pretty bad quality for web content, especially, and that's where sometimes the images of interest are sitting, right? We want to, and which we want to analyze, right? And again, with someone who knows what they're doing, can actually simply launder and do some filtering and make many of these forensics techniques sort of less reliable, right? So this, what we call counter forensics, right, is not that difficult, right? And for those of you, again, who are security minded, I run into this question a lot, saying, hey, I can defeat this, so what's the point, right? Forensics is a little bit different. Forensics is after the fact. In forensics, you are relying on the adversary to make some mistake, right? So you're putting the burden on not making the mistake on the adversary. When you're trying to secure a system, the burden actually, unfortunately, many architectures, many ways we have of protecting systems, sometimes the burden falls on us. We have to make sure that there's no hole, there's no sort of weakness in our security posture, because all the attacker has to do is find one weakness, right? And they've compromised the system. Security is strongest as the weakest link or whatever. Forensics things flip around a bit in the sense that now we are the ones who are searching, right? We are the ones looking for traces of mistakes, right? And if one thing doesn't work, you try another, you try another, you try another, and hopefully you'll find the mistake that the perpetrator actually made that will allow us then to give insight as to who, what, why, etc. The kind of questions that you're looking to answer in forensics. So just trying to give pushback to some of the very security-minded people saying, hey, yes, there is counter-forensics, but that doesn't obviate the need for forensics techniques. That doesn't invalidate forensics techniques. They're still needed, right? And so that sort of gives you a broad introduction. It's almost half my talk, right, about this whole field, right? And what has happened, say, but in the last 2, 3, 4 years, 5 years, right, things have moved on at a very dramatic pace, and it's all come from our ability to develop these neural models and machine learning techniques, right, that have allowed us to do what we call computational photography, and we can now, so essentially the camera pipeline that I showed you earlier slowly is being replaced by all kinds of neural models, neural pipelines, machine learning models inside the camera that can do amazing things, right? So all these HDR and things of that sort, we can take an image and really create a very realistic looking scene from it, close to what might have originally hit the camera. And we can produce images that are much better quality by using machine learning techniques, right? And in fact, I was talking to Payman Milanfar in one of our meetings, forensics meetings. Ed was there as well. And he was talking about how much of these things they do. They actually take 8 images for every single image, right? And they actually expect the hand to be shaking a bit because they get now 8 different samplings of the scene, and then they combine them together to get the final high quality picture, right? And the funny thing was that even if your hand is not shaking, they deliberately shake the sensor a bit because they want to sample the image to get the higher resolution, right? And he was saying that in 5 years, he thinks that maybe a lot of that processing that takes place, a lot of the components will be replaced by a machine learning model, right, within the camera. So, and these things kind of make our assumptions about forensics techniques, artifacts, etc., will make us revisit our assumptions, will make us revisit our models, will make things harder for us. Good news is, if you're a graduate student, there are lots of problems that will come up, and you'll be in business for a long time. So, right. And the earlier PRNU that I started talking about starts breaking, right? You don't see that PRNU quite well anymore when there's a lot of computation happening inside the camera itself before the final image is generated. So the idea then is that, well, perhaps this ability to compute inside the camera, right, and have neural models inside the camera, perhaps we can leverage that to enable or aid forensics as well, right? So about 2 years back, we started with that assumption and looked at what can be done. Did a couple of things which I'll talk to you briefly about, and then finally talk to you about something that we are currently working on, which I think has some potential, right? And again, the problem is not solved, but I think has some potential. And for those of you who might be interested in sort of working in this area, we have an open source toolbox, right? That allows you to simulate neural imaging pipeline and optimize it for different things, right? So So that allows you to experiment and simulate and test out different techniques. And we have all that available as an open source toolbox. And I think there's a pointer to it at the end. So the idea, one of the first ideas we looked at is that, okay, suppose that the camera pipeline is replaced by a neural imaging pipeline. It's just light in through the sensors, a neural network, and boom, the final image. I'm simplifying a bit, but suppose we have that kind of a architecture within the camera. Then can we optimize this neural network that takes the raw pixel data, right, the sense data, the intensity values, and finally produce that color image? Can we optimize that so that the image that is produced kind of has these artifacts in them, right? The traces that I talked about earlier, right, which were accidental. In the earlier case, okay, we put in filtering and we put brightness and we put color demosaicing and all that stuff. And whatever artifacts were there were accidental. But can we now design artifacts and put in them that will improve our ability to do forensics analysis? So we looked at like a pipeline of this form. We have this neural, and then we have there is a reasonably, and again, available in the open source, I think, a forensics analysis network, a neural model that allows you to detect whether an image has been manipulated or not with some accuracy. It has its limitations, but still, it's the best we have out there, I think. At least for, maybe things may have changed in a year or so, but at least a couple of years or 1 year back, it was the best we had. And then can we sort of train this neural model to produce images that work better with our forensics analysis, right? Intuitively speaking, that's what we were trying to do, right? And we showed, again, without getting into gory details, we showed that yes, right, we can actually train the neural image model so that operations like sharpening, Gaussian filtering, JPEG compression, resampling, etc., were detected with much higher accuracy, more than double the accuracy, as opposed to what was done with GAN, right, at a particular compression ratio, right? So it can be done. So that gives us some kind of hope. And the motivation behind this kind of an approach and this kind of thinking was that, you know, we need to do something proactive. Detection is good. Detection is required. Detection is always has to be done. But for certain type of content, perhaps we want to be proactive, right? Perhaps we want to put in artifacts in there that will help us detect. So for example, when we make $100 bill, we just don't make a pretty picture with the president's face on it, right? We actually put in artifacts in there that will detect counterfeiting, right? With our knowledge of counterfeiting, with the limitations of what counterfeiters can do, based on that, we put in some artifacts in there, which will help us detect counterfeits. It's the same kind of thinking. We're thinking, okay, what can we do that will help us detect, right? And again, detection is not always 100% guaranteed, but what can we do? I mean, how far can we get with this, right? And we showed that we could, at least in this particular restricted, simplified model, right? That the approach can potentially work, right? The second thing is then we looked at was, okay, we can change the neural image pipeline, but for that I need to convince Sony to do that, or Apple to do that, right? Can we do it outside that? Of course, even there you could, after the image is captured, you can put in an artifact. But can we do that, say, with a social media platform when you're uploading an image to their platform, they compress it, and can that compression technique be modified so that the resulting decompressed image is again forensics friendly, if you will, right? Because again, what is happening is that even in the compression world, a lot of our vanilla compression techniques, our traditional compression techniques, are now we are developing it's expected that perhaps they might be replaced by neural network-based compression techniques, right? So can we design a technique, right, that actually neural network-based compression technique? So raw image in, neural network, compressed image out, right? And neural network, decompressed image out. Right? So can we do that? Again, simplifying things. And we showed that that can be done as well, right? We can design compression techniques that give better performance than some of the other neural techniques out there, and better performance than things like JPEG, etc. In terms of image quality and compression ratio, right? And also at the same time provide better forensics analysis capabilities. So we can do that. I mean, again, it's just a demonstration of a simulated setting. That there is some hope here as well, right? We can even compress things with forensics in mind. And again, the quality, I won't go into details, but believe me, the quality is as good as anything else, and the bit rate also. So it compares favorably in terms of that signal to noise ratio and the amounts of bits that you spend, right? For more details, you can look at the paper. So we get pretty good rate distortion trade-offs, right, compared to. And so let me just run through that. And the third approach we started taking about a year back. It's been a challenging journey, and I think we're making some progress here. Is like saying, okay, so it is expected that not just the imaging pipeline, but now we are also have the capability to have a neural network in the sensor itself. So the sensor that which light falls upon, right, and from which the intensity of light is measured, right, that sensing element, right, pixel element, you can actually run a neural network on that element itself, right, a simple neural network. And so now we are right there at the time of image capture, right when the image is being converted from light to digital form, right, from optical to digital form. At that time itself, can we insert some fingerprint? Can we insert something in it that will allow us to detect that later on if that image gets manipulated after that, right? So, and such sensors are now sort of coming up, right? People are talking about that. And why would we want to do that? Because the PRNU, which was such a nice sensor fingerprint, the problem that it's just accidental. It's just something that we happen to benefit from, right? It just happens that physical sensors are actually all slightly different, right? No two physical things are exactly the same. But now we have the if we can actually design one, right, rather than inheriting one or simply using one, design one that is optimized for certain purposes, certain applications, perhaps that will result in a better fingerprint, right? And we can get the same. So we call them computational sensor fingerprints, right? And if you recall, the problem of the sensor fingerprint was, first of all, every image, the earlier PRNU sensor fingerprint was every image from that camera has the same fingerprint, right? That's an issue. So it can be spoofed, it can be copied, privacy issues are there, etc., etc. But if you use a neural model to kind of design and insert the sensor at the time of capture, right? You can imagine that perhaps there is this raw image content X, right? Taken before color demosaicing and things like that. And then what you do is based on a secret key, say, based on the context, what time, what place, whatever might be, time, location, content, etc., right? That the image was taken, you create, right? Based on that, you create a fingerprint, which is then embedded in the image before it goes into the imaging pipeline, and out then comes the final image. So can we do it right here itself. And then the image goes through the channel, right? People will upload it to Facebook, Instagram, whatever, change it, do this, do that. And then it sort of, now the question arises whether this image is authentic or not authentic, right? Well, if there is metadata that goes along, and assuming the metadata is there, right, like available, right, based on, and now we have an authentication service, say that's our model, right? We have an authentication service and in a very abstract level, the model, which can use the same key context based on that, can detect that, hey, this image is actually authentic or not, right? So, so the advantages are that every fingerprint on every image on every camera is different, right? So spoofing starts becoming more difficult. And now we have the luxury, if you will, or the ability, we have the opportunity to optimize it for whatever purpose we want to. So what do we want to optimize for? One is like detection, right? And yes, when you optimize for detection, right, we show that this computational sensor fingerprints do much better than a regular PRNU, right? A typical PRNU, computational finger sensor. We can design computational sensor fingerprints that will do much better. And again, it's through a sort of a neural pipeline, right? There's a feedback, and you design the computational fingerprint. And so, and just elaborating on that, as you can see, there's always a false positive, false negative sort of an overlap out there. But with PRNU, which could be high at certain compression ratios, even at these higher compression ratios, we can get good separation between the false image and when there is no fingerprint and when there is a fingerprint. And the visual impact is minimal. Although the interesting thing is that whereas something like the typical traditional sensor fingerprint was more or less kind of random noise in some sense, right? It turns out that the computational sensor fingerprints we design seem to have certain structure in them. And I don't know what the structures imply, or I don't know the answer to that. But clearly they seem to be different. It's just not but this is the kind of design that the neural network came up with, right? And the problem with all these machine learning techniques is sometimes they're a black box. You don't get an explanation of why, how, and we don't have one. And I know Purdue has such a stellar signal processing department. Perhaps someone will be able to use this to get better theoretical insights into what might be going on or what's perfect to do. So even there, you do have this issue of saying, okay, Nasser, you have this computational fingerprint, you took your image in the camera, it went through, right at the time of capture, you put the fingerprint, and now I have your image with that computational sensor fingerprint. But I know it's there. What I can do is I can extract it by filtering, extract the residual, and put it into another image, right? I can put it into another image and claim, and then make that image look authentic, as if it was taken in that same context. Yes, it can be done, right? And we've studied this, and I won't be going into details, but we've studied this in the various threat models, right? As to what does the attacker know, right? Attacker has black box, has unlimited access to the detector. Attacker has white box access to the detector. Attacker has a white box access to the encoder. Depending on that, we've sort of looked at what kind of success the attacker could have. But the most realistic model we were focusing on is the attacker simply has ability to query the detector a good number of times, right, before, in order to design that spoofed image, right? So that can be addressed as well. More recently, we've shown that if we do adversarial training, so in the training itself, you have these spoofed images also as a part of it, right? and train the detector to design, to be able to tell the difference apart, we are able to do that, right? We are able to reduce the success, right? Depending on the distortion, right? A lot of distortion does still creates problems for the detector. But depending on that, we are able to protect against some simple spoofing attacks as well. And we can take that one step further, right? We can, in order to again raise the bar on spoofing of this kind, we can actually make that fingerprint dependent on the content. So for the computer scientists in the audience, you can say, I can hash the image, and I'll create my fingerprint based on the hash of the image. So later on, when I try that on the image, the hash is clearly going to be different, and now you won't be able to do this, right? So given the properties of these hashing techniques. Sounds good, sounds interesting, but the problem is that images are strange animals. They can't be hashed that easily, because what are you hashing? Are you hashing the digital representation of the image? Are you hashing the content, right? Are you hashing the features, right? And it turns out that if you're just hashing the digital representation, if I change one pixel value, the image is really not changed and the hash is different. So, and when you're doing a query for authenticity, of course, the image would have gone through some changes. So question is, can you design hash functions that are robust to certain manipulations and not robust to too much manipulation? I know the problem is not very well defined, but there's a notion of fuzzy hashing been around in cryptography as well, in a very formal kind of way, right? And in this particular framework, the formal aspect of that is still weak, right? But practical fuzzy hashing techniques, or we call robust hashing techniques, signal processing, have also been have been developed, right? And mixing that in, combining that in with in using that to create the image fingerprint is giving us much better protection against attacks. And now suddenly the bar for the attacker becomes much more difficult, right? And here's just a baby example, right? So here is your test image, compressed reasonably bad, and there's a simple cut and paste. We put it just for a proof of concept, right? And with the proposed technique, we can actually nail down the manipulated region very well, right? But with PRNU, if we were just using PRNU, it still says that the image is potentially manipulated. Large areas turn up red, light up, right? But most of the areas that light up are actually not being manipulated, right? So we are able to get improvements in that sense. And hopefully we'll be writing this up in a month or so and making all this public. But I think it's an important step. It's still just a step. There's a lot more that should be done, can be done, I think, and needs to be done. So the lessons so far, I think the computational capabilities in intelligent vision sensors perhaps allow us to develop novel protection mechanisms. And it's our philosophy, or at least in our thinking, the earlier the protection is applied, the better, as the computer scientists in this field would understand. You want to reduce the attack surface, right? So the earlier you put in right at the time of capture, the better. And we're showing that potentially sensor fingerprints can be learned, right? Which are robust, provide very little image distortion, right? And they also have some security properties. And of course, the problem, of course, is giving provable guarantees of some of these security properties. That appears to be very, very, very hard. But again, many of our cryptographic techniques that we use don't have provable guarantees, right? But they have other sort of sort of properties that give us sufficient assurance that they are secure and they've been around for a long time. So I will not say that they are secure, but perhaps there is a way to get security out of them, right? And time will tell, right? And there is, interestingly, other work going on in this area, right? From a different direction. So Adobe is doing something very interesting called the Content Authenticity Initiative, but they're using the traditional crypto mechanisms, right? They're basically taking the image, hashing it like a SHA-1, SHA-2, whatever they want to use, and then doing a digital signature, attaching it, and having a provenance chain, using our normal integrity mechanisms that have been created in cryptography. And as long as the image stays within that ecosystem, these mechanisms are there, and you're able to say something about the authenticity of the image, or what was done to it, and who did what to it, etc. So it remains within the Adobe ecosystem. They are making the APIs open and public, right? This is not a commercial initiative by them. They actually want to make it all public, open source, so that people like you will be able to develop perhaps other interesting mechanisms than simply digital signatures, traditional digital signatures, and so I think that's an exciting opportunity, and I don't see any contradiction or any conflict between something like the computational sensor fingerprint and what Adobe is doing. It can be simply attached on if needed as an additional mechanism. So, and then JPEG also is actually, there's a working group, JPEG Fake Media. I urge you to join, participate. They're looking at what can be done to standardize some of these protection or provenance mechanisms. Of course, when they standardize, they're standardizing the syntax because they want to leave the algorithms themselves open to different people. They won't want to choke innovation. So, but they're nevertheless looking at standardizing the syntax for that. So, just to end, media forensics, for a long time, we have looked at detection. And as I said, same thing in security. For a long time, we were doing intrusion detection, right? But detection has limitations, right? It is needed, it's absolutely needed, but we have to go beyond detection as well. And in certain situations, for certain type of content, we perhaps need to explore proactive methods, and which I loosely call as secure capture. So can we do methods that allow us to do secure capture? So at the time of capture itself, something is done so that manipulation becomes more difficult after that. So let me stop at that. I think I went for 55 minutes instead of 50, but Gene gave me the license to do that. He said you can go a little bit over if you want.
Yep, you have a number of comments and questions.
Oh, okay, yeah, I was seeing them pop up because I was full screen. I couldn't stop and look at them. So there in Zoom, I stopped sharing screen first. In Zoom, I'll go to questions, the 8 questions. What is truth? Yeah. That's what Pontius Pilate told Jesus, I think. What is truth? I don't know what truth is. That's a PRF. What is PRF? Pseudo-random function?
I think the Purdue Research Foundation, and I think you were talking about Purdue's processing work, and that really was Ed Delp's group.
Okay. Yeah, so these are comments more than questions.
So you can click answer live and then done if you don't have anything to say to it.
Correlation is not causation, of course, right? Would quantum computing improve I don't know what quantum computing has. I can't see the connection with it, but that's because of my own limited knowledge about quantum computing. Uh, so, uh, DYS arts, what is that? I have no idea.
I think DYS is do it yourself. But I don't know. I don't remember what you were talking about when the question was posed.
Okay. Overlap with cryptographic authentication? Yes, indeed. The problem, of course, is there's not a direct transfer, because in cryptographic authentication, you're authenticating the exact sequence of bits, and here it's content, whatever that content means, right? And so that's what makes it a bit harder. Ed said, nice talk. So Ed said, can your ML approach be used to do a ream watermarking attack? So that is where we brought the content hash in it. And we believe that the content hash will make it difficult, but we've not spent time we will do that. We've not spent time doing that yet. But that's a great question. I mean, of course, one has to look at that. And of course, that's something we have to kind of demonstrate that, hey, this is more than demonstrate, actually convince people that this can't be done. And we've not done that yet. I don't know, Ed, you might have heard this talk of mine before. I'm trying to sort of get the community to look at it more, because there's this a lot of activity in detection. And as I said, detection is needed. But I think the other side of it also needs to be looked at. And because there's certain images, certain type of content, like police body cameras, right? And things of that sort, the pictures that journalists take. We need better guarantees of their provenance, right? Because otherwise, once fake media erodes trust in society, there has to be some what I call islands of truth, right? Some things that we can believe, and to get that, to build these islands of truth, we need some proactive mechanisms, I think.
I think one you skipped over is, so forensics all about securing evidence?
Really? No. Securing evidence is more for the what is called the chain of custody, right? And yes, in the forensics done by traditional law enforcement, right, where it is presented in a court of law, chain of custody is very important, right? And chain of custody can be built in, right? And we know how to do that when we analyze, and this traditional model of analyzing a disk and this and that, same things can be moved here. Forensics is also about developing techniques that tell us what might have happened, right? Because so I think, and my work goes more into that direction, about recovering evidence, finding evidence, right? And not simply, and of course, protection is important, right? Securing the evidence is important. But my work more has been in the other two areas. Lossy compression and image malleability detection. Yeah, kind of. That's what I said. You could spoof the PRNU. Yeah. And that's the whole point between computational sensor fingerprints. We want to make them hard to spoof. And Ed said no. I don't know what he said no to.
Well, we've hit the end of the time here. Thank you so much for visiting with us and presenting this information. This is a great way to end out the summer series. I'd like to remind everybody who's listening in that the recording of this will be up in a few days on our website, and starting in August 25th, we'll have the first of our fall security seminar series being presented. We very much appreciate everyone having spending some time to come in and join us. And Nasir, maybe sometime in the not too distant future, we can get you to visit us in person.
For sure, and same for you. Same for you, Ed, and others. I was not able to see the names of participants, but yeah, if you're in New York City, look me up.
All right, all. Have a great afternoon and enjoy the rest of your summer.
Yeah, thanks.
Bye for now.